These lecture slides are for part 2 of set 2. In this presentation, I'll talk about circuit design using NAND and NOR gates. Reference for further reading is textbook sections 2.7. We can always implement a binary logical function using NOT, and OR gates only. And this is what we have seen in our recent circuit designs. However, there are other types of gates that are quite useful. Examples include NAND and NOR gates. A NAND gate realizes a NOT AND operation, that is AND followed by NOT operation. A NOR gate realizes a NOT OR operation, that means OR followed by NOT operation. In some technologies, fewer transistors are required for NAND than AND, and similarly fewer transistors for NOR than OR. In this slide, I show symbol and truth table for NAND as well as NOR gates. So this is the symbol for two input NAND gate, and the algebraic expression for the output is shown here, and the truth table for the two input NAND gate is shown on the right. If you see at the rightmost column, which is the output of NAND gate, and you'll be seeing that this column is just the complement of what you'll be seeing in the truth table of an AND gate. Here I have symbol for two input NOR gate. This is the algebraic expression for the output, and the truth table is shown on the right, and here is the output of that two input NOR gate. Again, this output is the output column is the complement of what you'll be seeing in the truth table for an OR gate. In this slide, I show n input NAND and NOR gates. The n inputs to the NAND gate is shown here. The output is the algebraic expression of the output is shown here. The term in the bracket corresponds to AND operation, and that is inverted using this prime or complement. Similarly, the n inputs to the NOR gate is at the left, and the sums or the OR of those two n inputs are shown in the bracket, and that sum is inverted or complemented using the prime. In this slide, I show equivalency between some gates. So on the left, I have two input NAND gate, and here I have the algebraic expression for the output of that NAND gate. If we use De Morgan's law, then what I have on the left side can be written as follows. And the expression on the right side can be implemented using the circuit diagram I'm pointing to. And this circuit diagram is equivalent to the circuit diagram on the right. That's because each of these bubbles corresponds to the NOT gates that we have in the other diagram. Similarly, here I have a two input NOR gate, and the algebraic expression for the output of that NOR gate is shown here. If you apply De Morgan's rule, then this is what we get, and then the circuit implementation of that expression on the right is shown up there. And this circuit is equivalent to the circuit that we have on the right, or the gate that we have on the right. Now I'll be using the equivalency shown in the previous slide to redesign some circuits. So here I have an example circuit. This is actually an implementation of sum of products. The products are generated by these two AND gates, and the sum is generated by this OR gate. So I want to convert this circuit into another circuit where I will have only NAND gates. I can start with by just simply converting this AND gate to NAND gate. So to do that, I put inverters or bubbles here. Since I have put a bubble here, that means I'm complementing the output of that gate. So I put another bubble or another inverter, and conveniently, or on purpose, I put the bubble here. Similarly, to compensate this bubble, I put another bubble here. That takes us to this circuit. Now, what I have discussed in the previous slide, this gate that I'm pointing to can be replaced by this two-input NAND gate. So in the end, what we have got is a circuit where I have only NAND gates. So we have started here, and then we have come all the way to a realization where I have only NAND gates. Here I'm showing another circuit. This is again a sum of products implementation. The circuit is a bit complicated in the sense that we have an extra gate here. That gate is a NOT gate. Again, in order to have only NAND gates in my circuit, first I start with this AND gate. That means I convert this AND gate to NAND gate by putting a bubble here and another bubble to compensate the previous bubble. And as we have seen, we can have an equivalent NAND gate if we have another bubble at this input of this OR gate. Because I have just inserted a bubble here, I need to put another bubble on the same line before. Now, how to replace this NOT gate? If you recall, if we have a two-input NAND gate and say these two inputs are connected and say that input is A and say this output is B, then the truth table for this gate is here A, B. If A is 0, B is 1. If A is 1, B is 0. So this two-input NAND gate with both inputs are connected to single input is really an inverter or NOT gate. So we can use this concept to replace this NOT gate with a NAND gate, and this is shown below. So what we have here, this bubble or NOT gate is implemented using two-input NAND. This NOT gate is implemented again two-input NAND. And of course, this is equivalently replaced by what we have seen two slides ago. And this is a straightforward implementation. Next, I have a circuit which is implementing product of sums. The sums are generated by this layer of OR gates, and then the product is through this AND gate. I want to replace all the gates that I have in the circuit with NOR gates. To do that, I start with the existing OR gates, or try to convert this existing OR gates to NOR gates. That means I put bubble here. Because of this bubble, I need to have another bubble to compensate the complement. So I put it here and here. This leads to this diagram. And as we have seen before, when we're talking about equivalency, this gate can be replaced with this two-input NOR gates. So what we have achieved is this. We have a circuit diagram where we have only NOR gates. So in this slide, I have another circuit. This is also to implement product of sum. The sums are generated in this layer of OR gates, and then here I have an AND gate for the product. But in this diagram, I also have an inverter at the beginning. So like as I have shown in the previous slide, to convert these OR gates, I can simply put bubble here. To compensate this bubble, I put a bubble here, another bubble here to make this OR gate to NOR gate, and to compensate for that bubble, I put a bubble here. So that converts this part of the circuit to this part. Now how to actually convert this inverter to something that uses only NOR gates? For that one, again, I'll be using a truth table for a NOR gate where the inputs are connected, and so this is A and this is B, and you can easily see this is the truth table for this gate, meaning that I can replace this NOR gate, sorry, this AND NOT gate with a 2-input NOR gate that is connected at the input. So in the end, I have a circuit diagram where I have only NOR gates.